In this video, we're going to be looking at some examples from section 10.1. First one we're going to look at is find 2 square roots of 49. So there are two numbers that you could multiply by themselves to get 49. The first one is 7. We know 7 times 7 is 49. And the second is negative 7, because negative 7 times negative 7 equals 49. Now, I suggested earlier that you might want to memorize the first few perfect squares. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, 10 times 10 is 100, 11 times 11 is 121, 12 times 12 is 144. That's probably as far as you need to go memorizing. You might want to memorize 13 times 13, which is 169, I believe. But you do want to memorize those. It's really just handy to have those right there at the top of your brain, ready to go, so you don't have to keep trying to figure these things out on your calculator all the time. Second, we're going to look at simplifying a couple of radical expressions. The first one is the square root of 81. Well, remember, when we're asking for the square root of a number, we're asking for its principal square root. So we want the positive number that you multiply by itself to get 81. And that one is going to be 9. The second one, we want the opposite or negative of the square root of 16 over 81. So we'll keep that negative because it's outside of the square root. So whatever we get for the square root, we then take the opposite of it. And when you're looking at a radical expression like this, you can treat the numerator and the denominator separately. So we're looking for the square root of 16, the principal square root of 16, which is 4, and the principal square root of 81, which is 9. But then we keep that negative out there, so our answer is negative 4/9. Here we have a problem where we are given a function, f of x, is equal to the square root of 1 minus x. And we're asked to find the function value at negative 3. So we will put in negative 3 for x, and we'll get the square root of 1 minus negative 3. And subtracting a negative is the same as adding a positive. So now we'll have function value at negative 3 is the square root of 4. And whenever we have a problem like this, we are looking for the principal square root. So f of negative 3 equals positive 2. In these examples, we're asked to simplify radical expressions. The first one, we have the square root of y plus 3 squared. And just to show you how we can think about this, I mean, really you can think about the square root and the square kind of, in essence, canceling each other out. But if you're having a hard time with that, let me just show you this once. That y plus 3 quantities squared is the same as y plus 3 times y plus 3. And the square root is saying, what number or what expression can you multiply by itself to get y plus 3 times y plus 3? Well, the answer is pretty much in there because the product is something multiplied by itself. So the square root of that is going to be y plus 3. Now here, because we have a variable, and it's possible that variable could take on a value that would make that whole expression negative, we must give it absolute value bars. The next one, m to the 12th, the square root of it. I'll show you here what we're thinking. M to the 12th can be broken down because of the power rule, not the power rule, the product rule, to m to the 6th times m to the 6th. So its square root is m to the 6th. Now the question you need to ask at this point is, do I need absolute value bars around that? Well, m to the 6th can never be negative. Because it's an even exponent, even if m were a negative number, it will always end up being positive because of that even exponent. So we do not need absolute value bars there. Here we're taking the square root of x to the 10th, which is x to the 5th times x to the 5th. Now this step, let me be clear, you don't have to write this out. I'm just trying to show you where these come from. And that gives us x to the 5th. Now here we ask the question, do we need absolute value bars? And the answer is yes, we do. Because this is an odd exponent, and we could end up with a negative. And we want to make sure that we end up with a positive. In this one, we're asked to simplify the cube root. So we've moved beyond square roots and into cube roots. Well, the cube root of negative 27 is negative 3. And the cube root of x cubed is x. And we don't worry at all about positives or negatives when we have odd roots. You might want to memorize the first few cubes. And I'll just write a few out for you. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is, 125. And those are the ones I know off the top of my head. But you might want to write out the first, say, 10 perfect cubes and the first 13 or 14 perfect squares, and just keep those on a note card out when you're doing your work. It might help. Okay, so here we're getting into higher roots. We have 5th roots and 11th roots here. Well, the 5th root of 243, you may or may not know, is 3. And if you don't believe me, try it. 3 times 3 is 9. Times 3 is 27. Times 3 is 81. Times 3 is 243. Again, it's a 5th root. We don't worry about positives or negatives, and it's not, no variables in it. It's just a number. Okay? The 5th root of negative 243 is going to be negative 3. Because an odd power or an odd root with a negative gives us back a negative. And the 11th root of m to the 11th power is m. And we ask ourselves, do we need absolute value bars around that m? And the answer is no, we do not, because m could be a negative number or a positive number. We don't have that same problem with odd roots where both odds and evens end up giving us positives. So it's just plain old M. And the last ones I want to look at some fourth roots to just talk about a couple of complications. Okay? The fourth root of 81, we're looking for the principal, so that's going to be 3. The fourth root of negative 81 does not exist. Now you may have heard of imaginary numbers or complex numbers. So when I say it does not exist in the real number system. So it can't be simplified because right now we are working within real numbers. And the fourth root of 16m to the fourth. Well, the fourth root of 16 is 2. And the fourth root of m to the fourth is m. We want to make sure we have the principal root because it's even, so we're going to do the absolute value bars. And you can either do them like this, where your absolute values are around the entire thing, or you can leave the 2 out because it's already positive and just do the absolute value of m.